In the last section, we talked about energy being a product of heat and work. But truthfully, in chemistry, it's not the work so much we're worried about. In physics, they worry about the work as aspect of energy and not so much about the heat. But in chemistry, we focus mainly on the variable of heat because that's the one that affects us the most. The flow of heat in and out of a system is referred to as an enthalpy, and we represent that with a delta H for enthalpy change. Enthalpy itself cannot be measured, but only the change in enthalpy can be measured. All right, so when enthalpy changes, we call that the enthalpy of a reaction, and it's basically the difference between the enthalpies of the products and the reactants. When you have reactants, you have a certain amount of enthalpy involved, and then in the products, you have a certain amount of enthalpy involved. If you've lost enthalpy, if enthalpy has gone from the system to the surroundings or from the chemical reaction to the outside, then we have one system, and if we've gained it, or if energy is required in order for it to react, then we have another. Now, there's two things we go back to the same thing we just talked about in the last section, the words exothermic and endothermic. If delta H is negative, just like delta E was negative, we call that an exothermic system. So in that case, heat has been released to the surroundings. Again, bring back the example of the hot hand you used in winter activities and burning firewood. When you burn firewood, the combustion of the wood generates heat flowing outward. Therefore, it is an exothermic reaction. If delta H is positive on a chemical reaction, that means the heat has been absorbed from the surroundings, and we say the reaction is endothermic. Endo meaning to enter. Again, getting water changed from a solid to a liquid is endothermic because it requires heat energy. Chemical ice packs for sports injuries are endothermic because they pull in heat from the surroundings and they get cold, right, or they feel cold to your hand. These two terms are extremely important. Cannot express enough how important these terms are. Out of chapter 6, there's two terms that you get. It's these two, exothermic, endothermic. They are the basis of everything we are covering. Now, when we have them, because they're so important, we sometimes will attach them to a chemical equation, to what we call a thermochemical equation. And you'll see something written like this. So when we had chemical equations before, it was just the reactants and the products there. In a thermochemical equation, you'll have the delta H value attached to it, and that tells you quite a bit. Looking at a delta H value is important to a chemist because it tells them what kind of energy is involved. In this case, changing water from solid, ice, to liquid requires the addition of 6.01 kilojoules per mole of water. Now, to a chemist, again, I said that's important because it tells me everything. It tells me, do I require energy to do this? So do I have to add energy to get the reaction to happen? If it's negative, in this case it's positive, which means it is endothermic because the energy is going to be drawn in. If it's negative, that means it's going to release energy, and how much energy is going to release? Is it a dangerous amount of energy? So all those things are important to us. Now, it is also, looking at that, we can relate that stoichiometrically to the system. From the equation, we see that the conversion of 1 mole of ice to 1 mole of water requires the addition of 6.01 kilojoules of energy. Since delta H is positive, again, we know it's an endothermic system. Now, the 1 I'm getting is coming from the coefficients in front. So those coefficients are stoichiometrically related to the energy involved, and we will see in a few minutes here how we use that. Now, when dealing with these equations, there are several principles or guidelines that we need to look at that makes things important. The first guideline is that state of matter are important. You need to make sure you have your state symbols correct and included. In the previous example, you can see what I mean by that. If we didn't have state symbols there and there, this equation would make no sense. Changing water to water would look like it took 6.01 kilojoules a mole. You can see that we are changing water from the solid state to the liquid state. Different substances in different states have different enthalpy values attached to them. Number 2, coefficients in reaction are related to the delta H values that are attached. So in the equation I'm given here, the combustion of methane, CH4, in oxygen producing carbon dioxide and water generates negative 802 kilojoules of energy. The negative sign tells me that it's going out. It's going to release energy as I'm burning something. Every 2 moles of O2 is going to generate that much energy. Every 1 mole of methane is going to generate that much energy. So they are stoichiometrically related. We can use those as a ratio to figure out some stoichiometry and some energy, and we'll see again in a second. Guideline number 3 says if a reaction is reversed, the sign of the delta H is the only thing that has changed. The magnitude stays the same, but the sign has changed. So from this equation, we had methane reacting with oxygen to produce CO2 and water. Now if we reverse that and take CO2 and water down here and combine them to make CH4 and O2, we see the magnitude is still the same. It's still 802.4 kilojoules per mole, except now that it is positive. So when you reverse a reaction, the sign is the only thing that changes. And that, again, becomes extremely important as we move through this chapter. Now let's see how we use thermochemical equations to do stoichiometry, as I've been talking about. In our first example, we're asked to calculate how much heat would be given off if we burn 266 grams of phosphorus in the air, according to this equation. All right, so in this reaction, P4 plus 5 O2s produces P4O10, and then in that combustion, we generate 3,013 kilojoules per mole of reactant. So to solve for how much heat energy has been given off, we start with what we're given, 266 grams of P4. Just as we did in chapter 3 and 4, we can't do anything with grams. We almost have to always, when you're given mass in grams, have to change that to moles. So we go from grams to moles by using the molar mass. 1 mole of P4 equals 124 grams of P4. All I did there was take P times 4, so 31 times 4, and get that. Now, that will give me moles of P4. That's not what I'm looking for. I'm looking for how much energy it is. Now, here's the new part. From this equation, I can get what's called a thermochemical ratio. A thermochemical ratio, or thermal ratio, is the enthalpy value to the number of moles of substance you're dealing with. So in this case, there are negative 3,013 kilojoules per mole for every 1 mole. So 3,000, negative 3,000, 3,013 kilojoules for every 1 mole of P4. Had I been doing the oxygen, I would have put 3,013 over 5 moles of O2. All right, so from there, we simply use our calculator then, and we take 266, oops, go back to the pointer, 266 divided by 124 times 3,013 negative equals. And the answer is negative 55.06 kilojoules per mole. Actually, 55.1, we'll say, kilojoules. So if I burn that much, that's how much heat energy would be generated. 55.1 kilojoules would be given off. Now, let's look at another direction. Let's see if we can go the other way. If we are given a heat, and we know how much heat energy has been released or absorbed by a reaction, we can also calculate how many grams of substance be there. Well, you might think to yourself, why would you need to calculate how many grams of a reactant you had? Why couldn't you just weigh it out? Well, in some situations, you couldn't weigh that out. Oxygen, for example, in this reaction, we can't weigh out because oxygen is a gas in the air. It's just reacting and pulling in. So we want to figure out how many grams of oxygen is actually used from the air if we generated 2,015 kilojoules of heat. So in this problem, we start with negative 2,015 kilojoules were generated. And again, I'm keeping the sign because I know it's being released. All right. To get from kilojoules to grams, I'm simply going to work and reverse what I just did. I'm going to start now with my enthalpy ratio, or my thermal ratio, and I know that there are negative 3,013 kilojoules for every 5 moles of O2 in this chemical reaction. And I get that from the numbers in front. 5 moles is that many kilojoules. From there, kilojoules cancel out. 1 mole of O2 generates 32 grams of O2. So again, moles of O2 cancel out. So mathematically, with my calculator, if I take negative 2,015, clear that, negative 2, next case again, clear. Okay, 2015 times 5 divided by negative 3013 times 32, I get 107 grams of O2. All right, so as you can see, enthalpy values or enthalpies can be used on a thermochemical ratio or in a thermochemical equation. They are just as important as the coefficients. They're just as important as the reactants and products. You can use them to figure out some information stoichiometrically, just as we've done in the past.